Now we will discuss a very important concept of critical radius of insulation. Now what is the purpose of insulation? Why do you use an insulation? To minimize heat transfer. To minimize the heat loss or the heat transfer, you use something called insulation. Where do you use insulation? If you walk into a lab, thermal lab, where there is a steam engine working, from the boiler, steam has to come to the steam engine. So you use pipes to carry steam. Right? And if you just use a steel pipe with steam inside, the energy of the steam is going to be dissipated in the form of heat, which you do not want, because steam has to have that energy when it enters the turbine. Only then it can run the turbine. So what you do is, you put a lagging on the pipe, or you insulate the pipe. Right? So that's one application of insulation. And there are so many cases where you use an insulation. If you have an AC outlet, you see that the temperature of the refrigerant that is entering is going to be very low, and heat will enter from the atmosphere into the refrigerant, and the refrigerant temperature may increase. So to avoid that heat transfer, in a refrigerant tube, you also again insulate it. In an air conditioner, you can see that, right? From the outside to your room, you see that that pipe that is carrying the refrigerant is going to be insulated because you want to minimize the heat transfer. So what is the idea of insulation is, if you have a pipe, say we are going to assume it carries a hot fluid. This is a pipe, say it's a steel pipe or a metal pipe, which carries steam at 100 degrees Celsius. And the ambient is at 20 degrees Celsius. Because steam, this pipe, the metal pipe, is a very good conductor of heat, there will be a heat transfer from steam to the ambient. To avoid that, what you do is, you put an insulator, which is a bad conductor of heat. Say maybe you put plaster of Paris, or you put some kind of a material with low thermal conductivity above this pipe, such that the conduction heat transfer is going to be minimized. So you are reducing the heat loss by conduction. Because this pipe material has a high thermal conductivity, there will be high amount of heat that can be conducted. But if you put a material of low thermal conductivity outside, then the conduction heat loss can be reduced. But what we are doing is, the conduction heat transfer is reduced definitely. But what happens to the conduction heat transfer? That is definitely going to be higher, because this was the original pipe, right? This was the original pipe. Now, if there is no insulation, what is the surface area exposed to convection? That will be the surface area exposed to convection. Because of the insulation put, now this will be the surface area exposed to convection. Now, to reduce the conduction loss, you have put an insulation because of which the surface area exposed to convection is going to be higher. So the convection heat transfer is going to be more now. So there is a possibility that instead of reducing the heat loss, it may increase the heat loss. It will definitely reduce conduction, but it increases convection. Is that clear? So there has to be a compromise. You have to be very careful when you put an insulation. It is not a guarantee that whenever you put an insulation, the heat loss is going to be minimized. Because whenever you add an insulation, the conduction heat loss is minimized because you put a material of low thermal conductivity. But it increases the convection heat loss. So we are going to do a mathematical analysis to come to a critical radius of insulation. If you want the heat loss to be minimized, you have to put an insulation at least to that radius, so that the heat loss is going to be minimized. Up to that radius, the heat loss will start increasing. After the critical radius, the heat loss is going to decrease. So that is the critical radius of insulation. Now let's derive the expression for critical radius of insulation. The expression is there in the textbook, in the data book. Assume this is the steel pipe or the pipe of metal which is having a high thermal conductivity. Right? And over this, you are going to place the insulation. So the insulation, the K of the insulation is Ki, and the K of the pipe material is thick. Okay? And now I am going to use radii. This is R1, that is R2. R1 and R2 are the inner and outer radius of the pipe, and R is the radius of the insulation. Clear? So R is going to be a variable. I may start with 0, no insulation, and I may go with high insulations. R1 and R2 are fixed values. They are given radius of the pipe. For this pipe, we want to put a radius R insulation around the pipe, and R itself is a variable. Now here the temperature is T infinity I. The temperature outside is T infinity O. Now if you draw a thermal circuit, you will have convection, you will have conduction resistance to this pipe, then you will have conduction resistance of the insulation, and then you will have convection resistance outside. Here. So this is Ri, Ro, both are convection resistances. This is T infinity I and that is T infinity O. And this is the conduction resistance R1. R1 is due to the pipe. R2 is due to the insulation. Clear? Now you can write the heat transfer. The heat transfer is nothing but delta T by R. Now if I use this delta T, T infinity I minus T infinity O divided by Ri plus R1 plus R2 plus R1. Right. Now Ri is 1 by Hi into Ai. R1, you know the expression ln R2 by R1 by 2 by Al. R2 is logarithm R by R2 into 1 by 2 by Al. Ro is 1 by Ho into Ao. So we have this expression. Q is equal to T infinity I minus T infinity O by sum of all the resistances. Now we are going to see where the heat transfer will be a maximum. Delta T is a constant, that's a fixed, those are two fixed temperatures. Now Q depends on the resistance. And if you change the insulation, which resistances will be changed? R2 will change and RO will change. Why will R2 change? Because the radius of the insulation is changing. There is ln R by Ri, RO by Ri. The outer radius of the insulation is changing. So this will change. And RO will change because the area is going to change. So these two are going to change. So if Q is a maximum, then R should be a minimum. Right? If there is maximum heat transfer, then the denominator has to be a minimum. Now what is R? R is 1 by Hi Ai plus logarithm R2 by R1 by 2 by Kl plus logarithm R by R2 by 2 by K insulation into L plus 1 by Ho into Ao. Ao is going to be pi 2 pi R into L. So you can pause for a minute and then write all the resistances. Go look at the data book and write expression for all the resistances. This will be the sum of all the resistances. Now, if R has to be a minimum, then dou R by dou radius has to be equal to 0. For a function to be minimum, its derivative with respect to R has to be 0. Here R is the only variable that we have. Now, if you differentiate this, so call this as star, take a differentiate the whole equation star, both sides with respect to R. So you differentiate capital R with respect to R, you get dou R by dou R or dr by dr equal to, that's a constant. If you take a pipe, Hi is a constant, inner area of the pipe is a constant, only the insulation is changed. So this will be 0. R2, R1 are fixed, they are the pipe radii. 2 pi K, they are all constants, so this is also going to be 0. Now you have a variable here. R2 is a constant, that's the outer radius of the pipe. Ki is the thermal conductivity of the insulation, that's also a constant. L is the length constant. So all these are constant, where is the variable? R. So first keep the constants out. 1 by 2 pi KI is a constant. Now we have to take a derivative of ln something. Ln something is 1 by something into the derivative of something. So that will be the derivative of this, plus again here you see 1 by 2 pi h naught L is a constant. The derivative of 1 by r is minus 1 by r square. Now this has to be equal to 0. For a minimum, rho r by rho r has to be equal to a 0. So we take this term to the other side. There is a negative which we take to the other side. So you have 1 by 2 pi k I L. Here there is a cancellation of r2 into 1 by r is equal to 1 by 2 pi h0L into 1 over r square. See, there is a 1 by r2 and there is a 1 by r2, numerator and denominator, that will cancel off. And remaining terms are 1 by 2 pi KIL into 1 by r. This is taken to the other side. Because of the negative, it will become a positive. 1 by 2 pi h naught L into 1 over r square. Now you can cancel 2 pi and you can cancel L. Right? Becomes still simpler. And you can cancel this r with the r square. Now we want an expression for r. What is the radius of the insulation that we have to put? So r will take it to this side, all the other terms will take it to the other side. You have r equal to, you have a denominator h naught and this ki goes to the numerator, ki minus h. This is the expression for the critical radius of insulation. Now what will happen up to the critical radius is, ki will be a constant, right? It depends only on two things, the thermal conductivity of the insulation and the convective heat transfer coefficient. The outside convective heat transfer coefficient. So what will happen is, if this is the radius r, if you look at the heat transfer, initially you have one value of heat transfer, that is Q without any insulation, let me call it as Q star. If you put r equal to 0, if r is 0, that means there is no insulation, just the heat transfer from the pipe. This is the amount of heat transfer from the pipe. Now if you add insulation, initially the heat transfer will increase. This is because the convective heat transfer will dominate up to a certain point. After that, the heat transfer will start to decrease. Now where the heat transfer is a maximum, after which there is a decrease in heat transfer, this is called the critical radius of insulation. And this will be RC. So this radius is Pi by h naught. So what will happen? Initially you have Q star heat transfer without any insulation. When you start adding insulation, the heat transfer will start to increase up to a particular point. It will reach a maximum somewhere. That maximum heat transfer is at the critical radius. Now if you put insulation above the critical radius, the heat transfer will start to decrease. So that is the importance of critical radius of insulation.